Okay, so hi, I'm Rafael O'Halloran. In case you don't know me, I'm in the TIMI and BIC and radiology and psychiatry and all of these other things. Um, my background is in MRI physics, and so I was asked to give an educational talk at this year's ISMRM, so this is the talk that I'm preparing for that. I'll just preface it by saying it's in a session where the first two talks will explain how MR physics works and how you manipulate the spins using radio frequency pulses and gradients. So I'm not going to go over that here. We're just going to mainly focus on the concept of K-space and how it can be used to conceptualize how images are formed, acquired, and how the different MRI parameters affect the way the images will look in terms of K-space. So in the last talk that you would have seen if you had gone to Singapore in the future and sat through it, you would have learned about K-space as a way that images are expressed as a sum of what they called stripe patterns. And I kind of like the terminology. Formally, they're sine waves in 2 or 3 dimensions, but they really are like patterns of stripes. They're thin stripes, thick stripes, but you can build up images in terms of these, in terms of adding up these stripe patterns. And the reason why we care about this is because MRI scanners measure things in K-space. They measure things as a decomposition of their stripe patterns. And so the pulse sequences, they use RF and gradients to manipulate the spins in order to figure out what the combination of the stripe patterns you need to make the image that you are interested in. So here we'll build on that and use K-space to understand the way MRI images are formed and look, and how a couple of parameters will affect images and image quality. And by quality, we usually mean SNR. So that's what we'll focus on. So the outline, we'll talk about image space and K-space as the two sort of spaces that we care about. And I chose this nice zebra image because of the stripe pattern thing. It kind of inspired me to look at a zebra. And then in the second part, after we introduce that, we'll talk about a very simple pulse sequence and how manipulating some of the parameters affects what you're doing in K-space, and then how the image will look based on those things. And then finally, talk about SNR and practical ways to change SNR. So first, the spaces. So image space, when we think of image space, what we mean is it's an object described as a collection of pixels. And when we zoom in, we see that the image is indeed made up of a bunch of little squares that have properties that we care about, such as location and the intensity. In MRI, the intensity typically doesn't have units in MRI the way we mostly do it, but it's a number that tells you how bright the image is at that place. And I'll just warn you that during this talk I might use the words pixels and voxels interchangeably, but when we say voxel, we mean a volume element. When we say picture, we mean a picture element. One is 3D, one is 2D. We have to talk about things in 3D because the objects that we are interested in imaging are three-dimensional, so that's why we talk about a voxel. But if I use them interchangeably, my apologies in advance. So in K-space, as I mentioned before, it's a description of an object as a sum of stripe patterns. We can break the image down and visualize what these stripe patterns look like. Mathematically, this is called a Fourier transform, so sometimes you'll hear K-space called Fourier space. We won't show any equations. I was actually allowed one equation through the whole talk, I was told, but I didn't use it. So I was tempted to put that one, but I didn't. So anyway, the stripe patterns look like this. They're just bands of sinusoidal waves in 2 dimensions, or if we're doing 3-dimensional imaging in 3D, that's kind of hard to visualize, so we stick to 2D. Once you have these stripe patterns, you can then add them all up and build them back to make the image. And the little square I showed below the arrow is just those 5 stripe patterns summed up. So you can see how even with just 5, you can sort of build up a little bit of structure in an image. And if you use all of the ones that you need, you eventually get back the image you want in a process that's called the inverse Fourier transform. It's just the opposite of the Fourier transform. And this is typically what we mean when we talk about reconstruction or image reconstruction in an MRI. And interestingly, a lot of people that I know don't like the word reconstruction because the image was never constructed in the first place. You're constructing it for the first time. So these people say it should be called construction, but that's just an aside. So visualizing the the stripe patterns themselves can be a little tedious. So a lot of times you'll see K-space represented as an image like this in terms of just pixels. And in that kind of representation, each pixel just represents one of the many stripe patterns that we need to build the image up. So we have image space pixels, and we have these little K-space pixels. And they, like the image space pixels, have a location in K-space that encodes which stripe pattern we're talking about. So depending on where it is on this K-space picture, it determines which of the stripe patterns it represents. And it also has an intensity, which tells us how much of this stripe pattern we need to use to make the image. And then there's one more thing we have to tell in order to build the image up, and that's a shift of the stripe patterns. Because if I just tell you how wide the stripes are and which way they point and how much to use, you still don't know how to shift it. There's a degree of freedom there. So to describe that dimension, we need another number, which we call the phase. So in this way, K-space is sort of complex. You need two numbers at each point to tell everything that you need to know about it. And the phase is typically represented in degrees or radians because it's circular. The more if you start shifting the stripe pattern along, eventually you'll shift it so much that it's the same stripe pattern as it was before, because the crests will line up. So that's why it's a phase, it's a circular thing. And we'll talk about exactly how that works in just a second. So as I mentioned before, the location in K-space tells you something about the stripe pattern. And the direction of that K-space pixel with respect to the origin will tell you the direction of the stripe pattern. So the pixel I highlighted with this little circle, and so if you draw a line to the origin, that's the direction of the stripe pattern. And if I change where that is to the other quadrant, you see the stripe pattern changes, so this is the way that we encode the direction. And to encode the width, it's just the distance to the origin. So if I draw a dot that's close to the origin, that K-space pixel represents a stripe pattern that is wide, so they're broad bands, and then the one that's further out, away from the origin, is a narrower band stripe pattern. So now we've got ways to encode the direction and the width. And then, as I mentioned before, that intensity number, that value, tells us how much to use. So if it's low, if the number is low, we don't use so much of the wave. If it's high, we use more of it. And then finally, the phase. I think it's easier to see in 1D first, so I drew a 1D version of the wave, but if I give three different phase shifts, 0, 90, and 180 degrees for the same stripe pattern, all it is that wave shifted by whatever amount it is. And as I said before, if I go all the way to 360 degrees, I'll get back what I had at the 0 degree one. And in 2D, it looks like this. So at 0 degrees, you see the band is kind of across the middle of the image, and as you add phase from 90 to 180, that band moves away from the center. And because this is where the signal is going to be deposited in the image, you can see that it will affect the amount of signal that will go into your image, because in one case you have all this bright signal in the middle, and in another case it's on the outside. So the phase is really important. And the consequence of getting rid of it, I'll show you with the Mona Lisa here. Let's go from image space to K-space. So that's her K-space. And let's take away the phase. So I've zeroed out all the phase, and I just have the real part of the signal. When you do that, you get this image, which is obviously not right. And so you can imagine if you don't pay attention to your phase in an MRI image, you're going to get a brain that looks kind of like that too, or whatever part it is that you're looking at. So phase is important. Okay, so let's look how to build up an image from K-space. So I'm going to play this video, and what you're going to see is we're going to start from no part of K-space, and I'm going to grow a region from the very center and moving in a circular fashion outward, adding more and more of the K-space, and you'll see how the image changes. So we're starting to get the contrast here, the general features appear, the broader features, and then we start adding the finer and finer details as these narrower and narrower stripe patterns get added. And then you probably won't see any more change now because of the projector, but as you keep adding more and more, the image gets sharper. And we can do this in reverse so that you can see kind of the opposite effect. Now I'll take away the center in a circular fashion moving outward, and you'll see what that does. So let's cut away the middle. So you see the contrast goes away, the large features go away, most of the general fill-in goes away, and then now you're just seeing the details, so the edges and the fine details of the image, which tells you that they're sort of out there in the edge where these really fine-grained stripe patterns are, which kind of makes sense. So the take-home for that is that the details are in the outside of K-space, or at the edges. The edges of K-space have the edges of the image. And if you look in the center, that's where sort of the contrast lives. So if you just have the center of K-space, you'll have a blurry image, but you'll have most of the general gross features of it represented. Okay, so that's basically our sort of overview of how K-space works and the general features and parts of it. And now we'll move on to how pulse sequences move through K-space and how changing the parameters change the pulse sequences and then change the images. So this is my very simple pulse sequence. We'll go through it piece by piece. First, you need radio frequency pulse, the RF, to deposit some energy in the image, which you'll then listen to or read out later. So you need to give it some signal. And I'm going to talk about a 2D image, so I want to make sure that I'm only exciting one of the slices at a time. And in order to do that, I play out a gradient. In this case, it's the Z gradient, to sensitize the image, sensitize the excitation to just one slice of tissue, which is perpendicular to that gradient. And in most of the conventions, the Z is down the bore, so this is going to be an axial slice. When I play this out, I get an axial cut of the thing that I'm interested in. So this example will be a head. So let's turn that on the side and look in the XY direction. So this is an axial slice of a brain, which looks like a piece of chewing gum here, but that's because I can't draw that well. And now we'll look at the K-space of this object and how to move through it with the rest of the sequence. So just like the image has an X and Y direction, we have a KX and a KY that correspond to those two axes. And to move through them, I'll use gradients, magnetic field gradients. If I play out a little pulse on the Y gradient, that will take me up in the KY direction. So I've moved up a little bit in KY. And if I play out a pulse on the X gradient, then I'll move in the X direction. And I put a negative pulse here, and that shows you that I go to the left. So left is negative, right is positive in this convention. And if I do another one on X, then I'll go across K-space from left to right. And in this basic pulse sequence, this is how I'm going to read out the data in K-space for that one line. And then I have to do one other important thing. I have to turn on my ears and listen to the data that comes in order to record it. I have to tell the scanner when to record data. And so in this way, I can read a line of K-space, and I can repeat this and measure multiple lines of K-space, like that. So you can see in this way, the gradients are kind of like the knobs on an Etch-a-Sketch, and you can turn them and move yourself around in K-space by dialing in different pulses in the gradients. And this is how you can understand like how non-Cartesian sequences work. If you want to make a spiral, then you have to be good at doing the knobs at both times in just the right way to make a nice spiral. But for now, we'll stick to this, this rectilinear or Cartesian sequence. Okay, so now we have our sequence. Let's talk about some parameters that we can adjust and how this looks in our sequence in our K-space, and then later how it affects SNR. So first, resolution. When we say resolution, we mean basically the size of these pixels that are in our image. So in low resolution, we have big fat pixels, and high resolution, we have little pixels. And so no surprise, when we have big fat pixels, the image looks blocky, like on the left. And when we have high resolution, small pixels, we can see fine details you can see on the right. And if I zoom in on this wheel, you can see the consequence of this. At some point with the blocky pixels, I lose the resolution in the center of this little wheel. And it was made specifically to kind of show this in sequences. And so in K-space, this means that I need to go further out, because as you saw before, the details are on the outside, and the further I go out in K-space, the finer these stripe patterns are. So you can imagine if I want to represent finer structure, finer details, I need finer stripe patterns, and that means going out further in K-space. So if this one on the left represents my low-resolution case, and let's say this is the sort of furthest stripe pattern that I have, then if I go high resolution, I need to fill in more points in K-space, and then the sort of outside ones represent finer stripe patterns. So I'm acquiring more of these higher resolution stripe patterns to get the higher resolution. For the sequence, this means actually changing the way that I play out these gradients, because to move myself through K-space, I need to change the gradients. And so if I want to have a high resolution scan, I need to have more of these Y steps, so I go further in the Y direction. I need to have a bigger gradient X so that I travel further along the KX. So that looks like this. So see the points are out further in K-space. That means the gradients that I'm dialing in need to be bigger to move me all the way across in the same amount of, well, I'm showing it here in the same amount of time. You could extend the time, but this is another free parameter. And because I need more of these phase encodes, more of these Y gradient steps, it's going to take more time. So it's kind of, everybody knows this high resolution takes more time, but this is why. You need to actually sample all of these points. So high resolution, more steps, longer scans, and Kmax, or the max in K-space, determines what your resolution will be. Okay, what about field of view? That's pretty intuitive. The big field of view is a larger area over which you're imaging. Small field of view is a small area over which you're imaging. Obviously, this example is kind of a waste. I mean, you would never prescribe a ridiculously large field of view like this, but for the sake of argument. And practically, if I hold the resolution fixed, what this means is I need more pixels. So my bigger field of view means I physically have to decide what the values are in more pixels. I need to make more of these measurements to see what the values of these pixels are. And what that translates to is K-space density, because remember, the resolution was determined by my Kmax. So if I fix resolution, I'm not going to go out any further in K-space. So to make more measurements, I have to fill in sort of more densely in K-space. And this more measurement, more pixel argument is sort of my non-mathematical way to represent what's kind of difficult to represent without an equation. But it's basically that the number of equations that you have has to be equal to the number of unknowns in order for you to make decent measurements without assumptions. So the number of measurements you make needs to be bigger than the number of unknowns, and this is my crude example of that. Let's say I want to know the weight of a feather and a hammer. That's two unknowns. And then I do a silly experiment where I put them both on a scale and make one measurement. Obviously, I can't know the weight of either one with this technique. And so similarly, when you're making measurements in K-space, you also have to make the number of measurements equal to or greater than the number of unknowns that you have. And that's why K-space density has to go up when you have a bigger field of view. It's just, there's no other way to explain that without an equation, so I'm sorry. Anyway, so this is what the sequence looks like. Now, I don't have to go any further out in K-space so that the size of my gradients don't have to change. What needs to change is the number of steps I make in the Y direction, or in the phase encoding direction, and I need to acquire more samples in the X direction. So notice all my gradient sort of heights are the same, I mean, except for the intermediate steps in the Y, but the X is the same, and I've actually acquired more samples along the X. And this kind of points out something that is another degree of freedom, and that's the bandwidth, which I'll get back to in a minute. But basically this freedom to choose how often I sample along the X direction as I'm reading across, that's bandwidth. And like I said, we'll talk about the practical implementation of that in a minute. But for right now, the take-home for this field of view portion is that the K-space sampling density will determine the field of view. And this is based on this sort of measurement principle. You need to measure more to get more unknowns. So now I want to talk about another aspect of field of view that's kind of interesting, and that's this phase wrap principle. And so you might have seen this in a scan, and this is the nose and the back of the head artifact, named for obvious reasons. And this occurs when you prescribe a field of view that has a part of the anatomy outside of it, and particularly when that anatomy lies outside of the field of view in the direction of the phase encoding. And this can be problematic because if you do it in a bad enough way, you can have that nose be inside of the neck or in the brain or in a place where you're interested in, and then you have a problem. So why is this? Well, if we remember back to the description of K-space, we have these stripe patterns, and the stripe patterns are infinite. They don't get cut off at the end of the field of view. They just go on forever. So that means that our image that we build up out of all these infinite stripe patterns is also infinite. And if we look outside of our field of view, we see that it's just copies of the same image that we have inside of the field of view. We typically just represent one of these field of views, the field of view we choose, because we're not interested in seeing copies upon copies of the same image, but you can if you want. And that's because the stripe patterns are infinite. And if we do everything right, we sample K-space in a dense enough way to support the field of view that we ask for, then things are fine. We can just cut out the image that we want, and great. If we don't, if we sample not densely enough, then the copies get closer and closer together until finally they're overlapping. And so this is when we get this wrapping, this phase wrapping. It's because the field of view that we would like to have is not supported by the case-based sampling that we actually did. So this example is just sort of a cartoon to show how sampling density affects the spacing of the replicates. So if you're talking about prescribing a field of view on the scanner, is that right? So I guess the way to look at this maybe is that when you prescribe a field of view like on a scanner, what you're actually asking for is a number of measurements in the K direction, and that combined with the resolution determines this. So the dot spacing and the dot extent is determined by the field of view and the resolution. So when you ask for a particular field of view, that's what you're asking the scanner to do, and it sets up the gradients appropriately. And whether or not there's something outside of that field of view physically in the image is up to the operator to make sure that it's all contained in there. Otherwise, you may get this phase wrapping problem. So, and this example here is just meant to show that from the standpoint of the scanner, if you acquire too few of these dots, then what you get is the replicates, which are caused by these infinite stripe patterns, they get closer and closer together, and that's practically what causes the phase wrap. Okay, yeah, we can talk about it more, for sure. Okay, so moving on from this, if I point to a region now where these images are overlapping, this is kind of akin to this sort of silly experiment that I proposed earlier in which you measure feathers and hammers together. And in those regions where the images are overlapping, we have not made enough measurements to determine where the signal's coming from. So in that part of the image that I'm pointing to, I don't know whether the signal that's there is coming from the left or the right part of the brain. They're wrapped together. And in order to resolve them, I need to make more measurements. And so this process is also known as aliasing, which is just Latin for at another time, place, elsewhere, or under other circumstances. And it's when signal from somewhere elsewhere, wraps into an area where we don't want it. And the problem is, as I alluded to earlier in my answer, is that the field of view is too small. So I asked for a field of view that was too small for my image, and then my scanner, not knowing that I made a mistake, just set up the sampling like it was a small field of view, and then I got wrap. Now it doesn't happen like it happens as I just showed it here, because in real life, this only happens in one direction. So the question is, why is this? This is kind of interesting. And this has to do with the practical difference between phase encoding and frequency encoding. So in this experiment, I'll show you the difference. This phantom here on the right is a water tub, and I'm going to draw a field of view like the blue box that leaves some signal outside of the field of view in one of the directions, but not in the other. So in this first part, I'll set up my frequency encoding direction, that was X in the earlier example, to be the vertical direction and the phase encoding left-right. And when I do that, I see that I get a nice fine image with no wrap. So that's interesting. And if I flip the directions, now all of a sudden I have the wrap in the phase encoding direction, like you kind of expect from practical experience. So again, why is it in one direction and not the other? The difference is not really betrayed by the terminology that's typically used. So if we change the terms to discrete encoding versus continuous encoding, I think it's a little bit more clear. So in the Y direction, or in the phase encoding direction, we encode in discrete steps. Every TR we have to make a step in the Y direction, and then in the X direction we scan across in more or less a continuous way. So remember I told you about bandwidth, and you have to chop the signal up sort of at your convenience, or at whatever frequency you like. But when you scan across, you just scan across in an almost continuous way. Of course, it's limited by the hardware, but it's practically continuous. And then, depending on what sampling you ask for with your field of view and your resolution, the scanner sets it up so that it chops it up into these little bins, and then now you have this nice grid. But in that direction, in the left-right direction, you have essentially an infinite field of view because your density along that is very high, and field of view is proportional to sampling density, so you're able to support whatever kind of field of view you like there. And again, we get back to bandwidth. This kind of chopping up of the signal is determined by bandwidth. So bandwidth, as I said, you are free to determine how you sample your signal along the readout direction. You measure this in kilohertz or hertz per pixel. This is just a frequency, so how often you do it per unit time, right? Hertz, 1/2. Or sometimes they normalize it by pixel, which basically makes it the inverse of the readout length. Now, in the high bandwidth case, you can crank the bandwidth up, and then you get more samples per unit time, and you basically get more samples in the x direction. But this isn't the way that the scanner actually does things when you change the bandwidth. So it assumes something when you change the bandwidth. It assumes that you have decided already what your field of view and resolution are, and that you don't want to change them if you change the bandwidth. So if you change from the left situation to the right situation by dialing the bandwidth up, what it does is it fixes that case-based grid that you asked for at the beginning when you specified your field of view and resolution, and it ramps up the gradients faster so that you can get across case-space in the same amount of time, with the same number of samples because you're sampling faster. So in both the left and the right case, you have the same resolution field of view. You just go across case-space faster with the higher bandwidth on the right side. So it makes your readout short. So this can be good and desirable in some cases. Like, let's say you have a fast relaxation rate or something, and you need to get your imaging done fast at the consequence of blurring or off-resonance artifacts or something. But the fact that you've changed now your readout width is going to impact the SNR. And we'll talk about how that happens in the next bit. So on to SNR. So signal-to-noise ratio, how much signal versus how much noise. Practically, we mean when the SNR is high, we got a nice view of the image, and when it's low, we have sort of a grainy, noisy, crummy image. Then you only really need to know two things about this. So one is that when the scan time goes up, your SNR goes up. And it doesn't go up by the same rate at which the scan time goes up. It goes up just by the square root. So if you double your scan time, you get 1.4 times the SNR. We'll talk about why this happens on the next couple slides. And then the second rule of thumb is that when the resolution goes up, the SNR goes down. And this is linear with the volume of the voxel. So if you drop from 2 millimeters isotropic to 1, that corresponds to a volume decrease from 8 millimeters cubed to 1. So your SNR will go down by 8-fold. And it goes down in a linear way. So that we'll also talk about the kind of intuitive reason why that happens. So with the scan time, I have a specific way that I'm wanting to talk about scan time. I basically mean how long that data acquisition window is open. So the data acquisition window is the thing that I listen for my signal with. So it kind of makes sense that the longer that thing is on, the more SNR I get. And I have to do this in a smart way. I can't just turn it on and walk away and let it just sit on the same case-space point, because obviously I don't get an image. But if I do things right otherwise, the longer this thing is on, the more SNR I get. So there's three ways that you can make this happen. If you lower the bandwidth, like we saw in the bandwidth slice, you get a longer readout because your samples are further apart. And if you have the same sampling, then that means your readout increases. You can also do more averages, so just do this more times and build up signal averages. Or you can have more TRs, more phase encodes. This might happen if you change field of view or resolution, but it's something that contributes to SNR increase. Just having more data acquisition windows on. Okay, so why is it square root, not linear? So this is my kind of intuitive reason. The real reason why it's square root is obviously mathematical, but the intuitive reason why is if you take two averages. This is an example of imaging with a number of averages equals to 2. So my first image of the Mona Lisa is this noisy image, and I can think of it as being composed of the signal, the real stuff I want, plus some noise. And if I do this again, then I get another noisy measurement composed of the signal and some noise that I don't want. And the distinction here is that the signal each time is the same signal. I'm looking at the same thing. It doesn't change. But the noise changes. That's the nature of noise, right? So the more I measure, the more different realizations of noise I get. And when I average these out, the noise will average away slowly, but the signal will build up. So I get a better idea of the signal, and the noise is sort of slowly averaging away. So as I image more, I get better SNR, but not linear. It doesn't go up linearly because that noise takes a while to go away. But I am getting signal faster than I'm accruing this kind of noise, so it does go up. And so finally, the relationship between resolution and SNR. This is linear because the signal is proportional to the voxel volume. So the volume of tissue that the signal is coming from is proportional to the signal, and that's just because there's more stuff in there. There's more units of molecules that are relaxing. Any way you slice it, there's just more stuff, so you get more signal. But the noise is coming from everywhere, so the noise is the same. No matter what resolution you choose, you're going to get the same amount of noise. So the signal-to-noise ratio is just going to depend on the voxel volume, and it will depend on it in a linear way. So like the example I just pointed out before, going from 1 to 2 millimeter isotropic is an 8-fold increase in SNR because you've multiplied the amount of material that you're acquiring signal from by a factor of 8. So the signal goes up, noise is the same, SNR goes up by factor 8. And that's basically it. So I'll just wrap up with conclusion. K-space is a representation of image as a sum of stripes. The gradients, the physical gradients that you are imaging with move you around in K-space. The details of the image are represented in the outer parts of K-space, where the thin stripe patterns are. The contrast is in the center of K-space. And resolution corresponds to your maximum K-space value. Field of view corresponds to the density at which you sample in K-space. And the bandwidth is how fast you move through K-space while you're reading out your data. And all of this affects your SNR, where scan time gives you SNR at a factor of square root, and the resolution is linear. So you pay a big price for resolution, and if you try to get it back by scanning longer, you're going to end up scanning longer and longer and longer. And that's basically it. So that's all the people that have helped me with everything here at Mount Sinai. So I'd like to thank all of them. And any questions? I'll repeat. He told me to repeat the question, so I'll try to repeat them. Yeah, so the question is clarifying bandwidth and what it is. So at the end, my conclusion said that it was the speed at which you move through K-space, and that's because when you turn the bandwidth up, the scanner will try to compensate by increasing the gradients because it thinks that you don't want to change your field of view and your resolution. Now, if you actually had a thing that you could just independently change the bandwidth, then what that would do is it would ask the part of the scanner that converts the signal to digital to make more digital samples per unit time. So it will divide up that signal that you are acquiring into more smaller pieces. So what you would get then, if you had the same gradient, is you would essentially be increasing your field of view along that direction, along your readout direction, because you're sampling more densely. And you're also you're increasing the field of view by adding more pixels, right, along that direction. Right, because your resolution will stay the same, right? It's complicated on the scanner because you don't get to just increase the bandwidth, right? You rarely do, just increase the bandwidth. Other things will change to accommodate the bandwidth change. Well, you'll pay an SNR price because then you're essentially trying to gain more. If you try to make the voxel smaller, you get less signal per pixel. You get less SNR per pixel because the pixels are smaller, right? So you can do it, but you will get lower SNR. In fact, a lot of the older scans that I saw, especially the clinical ones on the GE scanner, would use anisotropic voxels because you could just do that, right? You could just use, for the exact same scan time, yeah, you increase the resolution in one direction with seemingly no penalty, but you will have lower SNR. It's just no way around it. Yeah, so typically the X direction is the frequency encoding direction, and as I've drawn it here, this is the frequency encoding direction. Well, it's not that it's necessarily faster in one direction versus the other. Usually the gradients all have the same specifications or roughly the same in each direction. It's just that in one direction you have to, so every TR you have to go to one place in the y direction. So each of these little rectangles that I'm showing you on the y correspond to one TR's worth of encoding. So sometimes you go up, sometimes you go down. So that direction is a slower direction in that you have to step through it in the TR loop and not in the innermost loop. Well, it depends wildly on the scan. So for some diffusion scans, you can have TRs on the order of seconds. For SSFP scans, you can have TRs on the order of milliseconds. Right, so the question is what is TE? And TE is just the time from the center